Where we'd left off last time was talking about some benefits of concurrency, and we focused on performance, trying to speed things up through running stuff sort of in the background, or maybe even running it in parallel so you can take advantage of multiple cores. So that's really about making the program more efficient or scalable. We also had talked, if you recall, about making the program be more responsive, so trying to do it so that the user interface can be talking and interacting with the user while other things are taking place in the background. What we're going to talk about now is how concurrency can be used to improve program structure in Android. And that's a slightly different set of concerns. It's more about software engineering in some sense than performance. In order to motivate this, let's first spend a little time talking about so-called event-driven programs. So many software programs, especially if you go back, sort of in the dawn of time of computing, were structured using purely event-driven models, event-driven programming models. So what the heck does that mean? And by the way, you can find some good explanations of these things at the links on the page, but I'll explain it now. What that means is the flow of control of the program is guided by events. So what does it mean to be an event? Well, with Android, which we'll get a chance to talk about a little bit later in more detail, they have all these states that your application or your activities can be in. And these are essentially events, right? So when your application first launches, there's a thing called a main activity. And an event occurs that the Android framework detects. It says, aha, this activity is starting up, or it's being created for the first time. And that event is conveyed to your code, your application activity code, by an onCreate hook method. And this is really just the template method pattern. And so it's calling back on your activity code, and it's providing a hook for you to say, this is what I need to do when this thing is initialized the first time. So think about onCreate as kind of an event. It's a hook method that gets called back in response to the created event, and it will turn around and provide a way to do essentially a virtual constructor to create that object. Once something is created the first time, it can go in and out of focus as you might bring other activities to the foreground and shuffle things around. And there are various ways to do that, through the task manager or through shutting stuff down or whatever. And an activity can launch another activity. So there's this concept separate from this, there's this event separate from the first time something's created for something to start. And so when an activity is about to become visible, the start event occurs, and the onStart method is automatically called back by the Android framework, and that provides your code a chance to do something in response to that. So you might allocate some data structures or create a thread or move something to the foreground or whatever. And there's a bunch of other events that happen during the lifetime of or life cycle of an activity. You can on-resume something, which is when it's about ready to start to run. And believe it or not, starting and resuming are different states or different events in Android. And then there's also the converse thing. You can pause stuff, you can stop stuff, you can destroy stuff. And all of these things are events, and the flow of control in the program of an Android application is driven by events. So it's an event-driven program. Here's another common example of event-driven code. In Android, what you do is you have a button that you want to allow someone to click, and the person can go and find the piece of code that's associated with that logical resource with that button. Let's say it's a download button or something like that. And so you can find that button, and once you've got the button, you can say to the button's click listener, here's some code to run when someone clicks on this button. And once again, when someone clicks on the button, the user interface toolkit will detect this, and it will arrange to dispatch the onClick hook method in response to that button press. So that's another example of events occurring and responding somehow to those types of things. This event-driven model is very, very common in user interfaces for some of the reasons we talked about last time, right? We don't want people to have to know about concurrency when they write UIs. We don't want to have to put locks in our code because that maybe makes it run slower, and so on and so forth. So event-driven programming is very, very common in GUIs. So in Android, as in most UI frameworks, we have a single event loop which runs in the main thread or the UI thread, and all the interesting things that application components, UI components care about are driven by callbacks to these objects or components that know how to handle them. All right, so that's kind of the way things work, right? Well, what's the limitation with purely event-driven programs? So for certain types of apps, or maybe more specifically certain portions of certain types of apps, a purely event-driven model is actually complicated to understand and may in fact be very inefficient as well. And let's take a look at an example. By the way, does anybody know what this famous painting is? The Scream, right? So this gets used a lot whenever I'm trying to show something that's, confusing or harmful. The Scream shows up somehow. So let's have an app that downloads and displays images from remote web servers, and I'll look at some other examples. And you'll also see that you often find rather comical pictures of me from many, many years ago when I had a cool mullet. I was going after the Def Leppard look in those days. So the idea here is we want to be able to download images into our program. And for those of you who took the last semester's class, we did just exactly that. So if we want to do this, if we want to avoid starvation of other things going on, right, like interacting with the user, we really don't want to have, or we cannot have in Android, blocking operations taking place in the UI thread. So downloading an image in the naive way of just saying, read or something like that, or get URI or get content or whatnot, those things will block. And that will cause problems. That'll cause the dreaded application not responding exception. So one problem is it's not going to work. And second problem is there's only one thread of control, right? So there's two problems. It's hard to understand and it's inefficient. Now, if you want to be purely event-driven, what you need to do is you have to take these long-running operations and then run them in little chunks where each chunk is done asynchronously. So what you would do is you would post a message to the message queue saying, I want to download this image. And what would happen under the hood is that there would be an asynchronous read requested, and that would try to read the first chunk of the image. Now, it's not going to block. It's just going to do the first read. And usually that'll get you, some number of bytes, whatever happened to be sitting in the socket that could be read in one gulp without having to block the program. So you'd have to put your socket into non-blocking I/O or use some kind of asynchronous I/O operation, and you'd read one chunk. And when that thing was finished, the result would come back as a message in the event loop saying, I read a small chunk of this file. And you'd say, OK, thank you very much. And then you would go ahead and say, how much did you read? Well, I'll subtract that off the amount I want to read, and I'll go and read the next chunk. And so you would keep this going on over and over again to do lather, rinse, repeat. You would keep doing these asynchronous reads or non-blocking reads one little chunk at a time over and over and over again until the entire image was downloaded. So that's typically how you would write this program if you couldn't block. And the thing to notice, and I don't really show the code here because it's actually somewhat complicated to do this in Android, but you could, and it's intentionally hard to do it because it's a pain in the butt. There's a disconnect between getting the next chunk and asking for the chunk after that. So there's a disconnect in both time and space, right? They're going to occur at different points in time. And if you look at the code, they probably occur in different parts of the code. The part that starts the asynchronous operation and the part that gets the result will be in different parts of the code. So if you look at the code, you're like, what the heck is going on here? It's very, very complicated to keep track of all this stuff. So one of the consequences is if you write purely event-driven code, it often leads to either spaghetti code, where it's strewn all over the place, or what we also call a big ball of mud. And you can read about spaghetti code and big balls of mud here at these links, and they're actually somewhat interesting to read about. And sadly, most code in the real world is written like this, but not our code. Our code will not be written like that. So why is this hard? Well, it's hard because there's very little structure or linear flow of control to help guide developers. You have to keep putting state off to the side and handle the results of asynchronous calls. So the problem here is that single-threaded event-driven programs can obscure the flow of control in time and space. That's kind of the main problem. And what's going on here is that the flow of control is bouncing all over the place in the software, and so it's difficult to get your head around what's happening. For those of you who took CS 891 in the fall, you'll recall we had talked about asynchronous programming with completable futures. And that was a sort of a variant of this approach, which is also a bit complicated to understand at first glance, but because it's working with a really cool framework called the Completable Futures Framework in Java 8, and because they've got these cool things called lambdas, and because they have thread pools and all this other good stuff behind the scenes, it's at least tractable, right? Although it's a little bit complicated to understand. But the whole issue here is bouncing back and forth between things is hard. And it's also hard to maintain code written like this because any small change will often break a lot of stuff because of these non-intuitive dependencies between different parts of the code that are split apart in time and space. Now, if we had a longer class, like a 20-week class, I would give you the chance of writing this kind of code, and then you would have a deep, intuitive understanding of why it's a pain in the butt. For right now, you'll just have to take it on faith. So let's talk about how we can simplify program structure using concurrency. And what this will allow us to do is it'll help us to overcome some of the drawbacks with purely event-driven programs. And in particular, it's going to make things more intuitive, arguably more intuitive, and you'll see why in a second. And it will undoubtedly scale better than the purely single-threaded event-driven approach because we'll be able to have multiple threads of control running, some of which are downloading files, some of which are responding to the user interface, some of which are doing other things. So it's going to be more responsive and more scalable and ideally better structured as well. So what we're going to do is we're going to take operations that are going to run for a long time, and we're going to allow them to block synchronously. And this is going to simplify some aspects of the code. And the reason why it's going to simplify some aspects of the code is that synchronous blocking within a thread often yields a more natural and collaborative control flow. Does anybody know why that is? What is the thing about blocking, allowing blocking in a thread that helps to simplify things to some extent versus an event-driven approach? Bruce? Absolutely. So it's linear execution, but even more specifically, what is the ability to block in a thread by you? Why is it more linear? Yes, it is absolutely more linear. I can totally agree with that. At least one stream is more linear than other streams running other threads. But what is the thing that's really giving you the benefit? I kind of had hinted about this earlier. Yeah. Yes, you're right. Dependencies are easier, but specifically, what is it about blocking threads that are a win in some cases? Yeah. 3. So context switching will definitely be an issue. There are pros and cons to that, but that's more of a performance issue. I'm thinking more logical about the logical structure of the program. What's the thing that a blocking thread gives you that an event-driven approach wouldn't? Yeah, Amanda. You guys are all real close. There's something very specific about what happens when a thread blocks. What's the context in which it blocks? If anybody has taken the programming languages course, hopefully they talked about this. I don't know whether they do or not, but well, here's the deal. When you have a blocking thread, any state that you have tucked away in local variables within the activation record of the method that you're calling, right? If you're in a method and you've got some local variables and you stash values in them, and then you make a blocking call, like let's say you have an integer that keeps track of a few fields, or you have some fields that keep track of some state, and then you call download file and you block. When the download file call returns, all those state in those local variables will still be exactly the same way as when you left to make the call. And that's the way that a runtime stack of activation records work. That's why I hope they cover that in the programming languages class, if you've taken it. So when you have a programming language like Java or C++ or C# that has a stack-based execution model, every time you make a method call, it pushes a new activation record onto the runtime stack. And anything that was in the previous activation record is kind of pinned underneath the new record. But when the new record finishes and pops off the runtime stack, all the state is waiting right there, boom. So it's convenient, it's linear, as you guys were saying. With asynchronous or event-driven programming, you've got to stash the state off to the side and then do an asynchronous call because you can't block. So when control returns to you, you have to fish out your state from somewhere. It's not on the stack because that stack is being shared by multiple asynchronous calls. And you then have to restore your state explicitly. So it's just extra work to try to keep track of that kind of stuff. So that's why the blocking approach is often a win, because the state just keeps where it was, and when you get back from the call, it's still there, and you just keep going. So Android has something called the Hammer framework. Remember, Hammer stands for handlers, messages, and runnables. And that's a concurrency framework that can help to simplify programming structure. And here's the way it's going to do this. And we'll talk more about this in the upcoming lesson. So you have a background thread, and that's where you're actually going to do the downloading of the file. And so operations that run for a long time, file download being one of such things, can be put into a background thread, which is really what we were talking about the other day when we discussed what's concurrency, right? We talked about how concurrency allows you to have operations running in the background that are going to be able to get the results back and then pass them to some foreground thread. Short duration operations, in other words, operations that do not block, will run in the foreground thread or the user interface thread. And most of the time, those operations, their purpose in life is to get the results from the background threads and then display them, or get something from the user that's very quick. And what's cool about this is the Hammer framework supports a hybrid half-sync, half-async programming model. And you can read more about the half-sync, half-async pattern that is embodied by this here at this link. And part of it's event-driven, the part that's the UI part, in a single thread driven by callbacks, and part of it's concurrent, running in threads that run in the background. So the nice thing about this is we don't really have as much spaghetti code, we don't have as much big ball of mud, because the app is organized in a more linear structure that doesn't bounce around quite as much, because the long-running operations that block run in these background threads, and then when they need to communicate something to the user, they put it into a queue, and it pops up by a callback in the user interface thread. There's a whole pile of patterns that embody this architecture. You can read about them in some of these books. Some of the interesting ones would be things like command processor, which is really how the background thread or threads talk to the user interface thread, active object, half async, half sync, half async, etc. These are patterns. We may or may not have time to talk about them in detail towards the end of the course, but that's where they are, and you can read about them here in these books and other resources. All right, so that's kind of an overview of the benefits of program structure from using concurrency. Most of our discussions so far have been rather conceptual, which is good because it's important to understand concepts. But if you're like me, I always feel a little better if I see some real code at some point before we go too far into these topics, because it's nice to see how it really works in practice. So this last part of the lesson will talk about how we're going to apply all the things we've talked about, the concurrent approach for downloading things in the background, in conjunction with the event-driven calls for doing certain UI interactions, in order to be able to build a little case study app. And this app is going to download an image from a remote web server and then display it to the user. So you give it a link and you can download it. So let's take a look at the app, and you can actually get the source code to the app if you want to take a look at it. And the way it works is it's got a little user interface, and you give it a URL, and then you can hit the download button, and then it'll pop up a little dialog saying, I'm downloading. In this case, we're using the Hammer framework. We could use other stuff as well. And it'll be doing the following things. It'll go out to the web, to some web server somewhere in the cloud, or here at Vanderbilt, and it'll download the image. And then after the image is downloaded, which can run in the background, and at least in theory, if we built the app slightly differently, we could have multiple images downloading at the same time, using multiple threads on multiple cores. Then, when it's all done, the image will be displayed to the user in some way. So this is kind of what the code looks like, and I'm using Java 8 stuff here. It's easy enough to do this with Java 7. And the reason we use Java 8 is it's just so much more concise. I originally had the example with Java 7 style code, and it took up a lot more space, and it was confusing. So now we just winnow it down to the bare essentials of what goes in the Lambda. So we're going to go ahead and have a thread that's going to do the work. And we're going to go ahead and start that thread. Remember, this may help with your programming assignment. When you make a new thread, it doesn't start to run. It just makes an object. It's not until you say start that things get interesting. And when you call start, a new runtime activation stack will be created for you. This is all under the hood by the Java virtual machine and the Java class libraries and the Android Linux kernel and all that good stuff. So there's a bunch of things that take place under the hood. When you call start, that creates a thread. And then the run hook method will get called back on the runnable that's provided, or the thread that's provided as the entry point into this new execution unit. And we'll talk a bit more about that. So just remember that you have to call start to get things going, and once start is called, then the code that gets run will be invoked. And I'll talk a lot more about this. We'll cover Java threads soon, and you can also watch the videos if you want a head start on that. Okay, so we're going to use the Hammer framework in order to be able to run that thread that we created in the background and then communicate the results back to the user interface thread when we're all done. And you can take a look at the Hammer framework. And this is one of my small little contributions to the field of computing is I invented the word hammer. So that word didn't exist until I started teaching MOOCs. And I was like, how do I explain this crazy framework which has handlers, messages, and runnables? And I said, aha, I will use the acronym HAMMER. And even more importantly, I have an icon. Does anybody know what hammer that is? What's it called? Oh, come on, guys. Mjolnir, or whatever it is. If you're Norse, you could probably pronounce it better. That's Thor's hammer. So the downloading of the image is done in the background thread or threads, and then it's displayed in the UI thread. This particular solution is intentionally defective because it doesn't allow you to interrupt the thread that's running. It doesn't allow you to do other runtime configuration changes. We'll cover those things later in the course. This is just to show concurrency. All right, so again, just a quick recap. The purely event-driven solution was not very cohesive because there was this disconnect between invoking asynchronous operations or non-blocking operations and collecting their results at some other point in time and space, which bounced around a lot, like Tigger, if you recall the earlier discussion. This approach, in contrast, is much more cohesive in time and space. And so let's take a look and see what it looks like. Here's the entry point method. When we click on this floating action button, or FAB, which is a material design widget in Android, in the material design paradigm, when we click on that button, that will cause this download image method to be invoked automatically. That's what the framework does for us. And we do that by some XML file magic to connect these things up. What happens here is that the download image method gets the URL that's entered by the user, shows this dialog saying downloading is in progress, and then it goes ahead and initiates the downloading of the image at this URL. So we're going to focus now on the start download method. Here is start download. So this is the method that's actually going to do the downloading. And it's kind of cool because it's going to show both how to do things in the foreground in the UI thread and also how to do things in the background in a Java thread that will run concurrently with the UI thread. So what we do is we define a lambda expression. So the lambda expression here is everything after the arrow and between the open curly brace and closed curly brace. So this is just a piece of code that will be grouped together and passed to the thread object so it can run in the background. Right, so that's what the lambda does. And then we call start on the thread. Notice this is also an anonymous thread. You don't have to do it this way, but it's just the easy way to show this on the slide. So we make a new thread, we give it a lambda expression, and we say start. And that causes the runtime stack to be created, and we'll go ahead and start to do the processing. And what the processing will do is it'll run the code inside the lambda expression. So you can think of what this lambda expression is basically the anonymous run method. It's the implicit run method on a runnable. So what this will do is this will call download image. Note this is taking place in the background, right? It's taking place in a background thread. So it's going to download this thing, and it's going to block. So this call can block. When the image is downloaded, it will get back the URI to the image. The image itself will be tucked away somewhere safely in the file system on the device. we'll get the URI to it. And then what we're going to do is we're going to call another method called run on UI thread. Now, download image was a method that we wrote, or someone gave to us. Run on UI thread is a method that's defined in Android as part of the Hammer framework. And what that does is it creates a command, and the command is just going to be this lambda expression. And it takes that command and it passes it over to the UI thread using the UI thread's message queue. So this thread will take that lambda, plop it onto the message queue. The background thread will then evaporate. It doesn't need to stick around. We could use a thread pool if we wanted to, but in this case, we just made a thread. So it'll evaporate, disappear, and then this lambda expression will be stuck onto the message queue. The UI thread will say, aha, there's something for me to do. I wake up. It'll pull that lambda, which comes through as a message on the message queue, and it'll call back its run hook method, because that's a runnable after all. And that will then go ahead and display the image in the UI thread. And at this point, there's not much to do because we've already downloaded it. And so it's just about sort of, flinging the image to the surface of the display. There's actually a component layer or component subsystem in Android called the surface flinger. And its purpose is to fling stuff onto the surface. So it'll fling the image onto the surface. So that's basically what's going on. So pretty cool. If you think about it, these methods, download image and display image, run in different threads. This runs in the background thread. This runs in the user interface thread. But notice how cohesive they are in time and space, right? You can look at that code, and once you know the semantics of the framework, you go, oh, OK, I'm going to download something in the background, and then I'm going to fling it to the surface of the display in the foreground thread. But both pieces of code are very closely cohesive and close together in space, and they actually run at different points in time, but you really can't tell that. I mean, they're cohesive, so you can see what's going on easily. So this approach is going to be a lot easier to understand than a purely event-driven version, which I didn't really show, since it doesn't bounce back and forth. It's all localized in one nice, clean way. All right. So that's a concrete example of what we're doing here. That example also will give you a few clues at how to implement portions of your programming assignment if you haven't already got them working.